করতে জানি রিফ্রেশ করতে হবে এখন ঠিক আছে নাকি আছে তো
நான் சொல்றது கேக்குறியா? சிக்கனை சாப்பிட்டு அதை சாப்பிடு. புரியுதா? ஏன்னா சிட்ரிக் ஆசிட் இருக்கும்ல, ஏழு
hello everyone. So we are going to start our meeting, this session. We will go further into the bandits algorithms, and we'll solve some problems on those. Just wait for a few minutes. Okay, so let's get started. So these are the problems that we're going to solve here. So first question is on PAC algorithms, the bandit algorithm, and using median elimination. Okay, to get the PAC arm. Okay, so this is the question. So how many samples will be required using the with the median elimination method we need 6 rounds. Okay, so for the naive approach, how many samples would be required? Okay, so this is the question. uh, so the point is that uh, so there are 6 rounds of median elimination to get this to get the PAC arm. Okay, so in median elimination what happens is that you know that the number of rounds or number of steps required is logarithm of number of arms in median elimination method. Okay, so logarithm at the base 2 of number of arms is this. Okay, is 6. Okay, that is what is given to us. Okay, so number of arms that are there is number of arms is equals to 2 to the power 6 is equals to 64. Okay,
Excuse me, sir.
okay.
Sir, I have doubt in assignment week 3, sir.
Week 3. Uh,
Ah, the
so
previous assignment.
previous assignment.
Hmm.
Okay. So okay. So so week three problems will come up after this. Okay. But
Okay, sir, fine.
we'll continue with the PAC algorithms first. Okay.
Okay, sir.
Okay. Yes. So number of arms is equals to 2 to the power 6 equals 64. So as you know, the number of steps required uh, is log k. K is the number of arms. Okay. And what happens in PAC algorithm is that so we are going to reduce the number of arms that are there after every steps until we are left with in the median elimination algorithm until we are left with one arm only. And so how many samples we take in the first step is like it's given by 1 by delta by 2 square log of 3 by delta L. So these are the number of steps that are taken. Okay. These are the number of arms that are taken for every arm, the number of steps. Okay. And likewise you update until delta L becomes equals to 1. Okay. So the number of arms is this. Okay. 2 to the power 6 equals to 64. And so moving forward, um, so next we are given this epsilon and delta, what is the how many samples would have been required. Okay. So from the naive approach, the number of samples is given by this 2 epsilon square and ln 2k by 8. Okay. So this is the our how many samples are required in the naive approach can be got by this. Okay. So here k is the number of arms, which is equal to 64. Okay. So that this becomes 128 divided by delta. Okay. So delta is 1 by e, and ln and 2 by epsilon square. Epsilon is half. Okay. So this becomes 8. Okay. So this is the expression we get. Okay. And simplify, you can get it like epsilon here. Okay. And this gives you the value D option. Okay. In this case you can check the calculation. So this is all we had to do here. So in the naive approach, the arm, for each arm this number of samples is equals to this. Okay. And then we have to uh, maximize QA to get the best possible arm. Okay. And so just a little bit of extra knowledge, like in the naive approach, the uh, time complexity for selecting the optimal arm is k by epsilon square, epsilon log of k by delta. So what we do, that we reduce the time complexity. Okay. So you can see the time complexity measure depends on k. Okay. Because k is the larger number of arms value. And if you reduce if we have to reduce the time complexity to make a more efficient algorithm, we need to take out the k, okay, and or to reduce the k or something like that. So so in the naive approach, this k is there in the inside the log, so we take this k out, and in the median elimination algorithm of the for PAC bounds, okay. So in the case of PAC bounds, just this log k by delta, in place of k by delta you'll get 1 by delta, okay. So that is one important thing. And okay, so this is the motivation of the median elimination algorithm, to reduce the time complexity of the naive approach, okay. And okay. So the median elimination method tells that, like uh, so first we are starting with delta 1, which is the number of arms in the median elimination method, okay. That is what I'm explaining. So number of arms, okay, and epsilon 1 is equals to epsilon by 4, like that, and del 1 is equals to del by 2, L equals to 1, okay. So these are the so so we sample every arm this many times, which I had shown previously. 1 by delta by 2 square log of 3 by delta L, okay. Next, so this is denoted by this expression, number of samples that we have taken is denoted by QLA, okay, for specific arm A, okay. So the median of this value is denoted by ML, okay. So next we write that so as you can see, so SL first started with SI means S1 started with the number of bandit arms. So the update rule here is the next what we have left, okay, means S2 in this case from S1 will be SL, means SL plus 1 is SL by uh, okay, uh, only those A's which satisfies this expression QLA, and so only take those arms, okay, which this number of samples is less than the median, okay. And after that we have update the epsilon SL and L plus 1. We do this until we are left with only one arm, so SL becomes is equals to 1, okay. So this is the algorithm of the uh, median elimination method, okay. And the naive approach is also there. Okay, so moving on, so proofs are also there in the lectures, okay. Now moving on, in the median elimination method, so in the median elimination method, the lemma states that I mean, so so the lemma states that for every phase, means like first we are taking L uh, means like up to L steps, okay. The median elimination method, we have So I'm going to write the preferable situation, okay, in which to select the optimal arm, okay. For that, the thing is the probability we are taking, we are maximizing this qj, okay. J belongs to SL, okay. So SL is, so among the arms that are left in the SL, okay, at lth step, J is one of that arm, so qj, we are maximizing qj, okay. And so and okay, and I belongs to SL plus 1. So the point is this, that we're looking at this probability, okay, and so this is less than, without the epsilon, this one is less than this, okay, but we are adding a little bit of epsilon value to make it close, okay, little close and little bit higher, okay. So the point is that at the L plus 1th step, the arm that you're taking, okay, so this is I actually, so the maximum of that, okay, and means like, and it is this expression, okay. So this one, the previous one is little higher than uh, the newer step, okay, the maximum value, okay. So that probability, or it is close, the ideal situation is this, that is equals to 1 minus delta L. It's a good probability. Delta L is small, so this is like very close to 1, okay. Okay, so this is the lemma of the median elimination algorithm, okay. So upon analyzing this lemma, we can get the answer. uh, so so as you can see, it is the maximum of the reward of the true best arm in SL, that is in Lth phase, okay, and it is the maximum of the rewards in L plus 1th phase, okay. So that is what is written, okay. So answer is 1 and 2. Okay, any doubt? Oh. Sorry, like I could not see their request here. uh, Finally saw the request, I admitted. We were covering the PAC bounds, okay, and the median elimination method. uh, for uh, for this expression to be true, what are the statements, what will be the A and B. So given from the expression, you can see, so this is the good situation to get the our optimal arm, okay, and so this is the maximizing, so this is maximize a maximum of the reward of the true pressed arm, okay. So this is the maximum of the reward of the true best arm SL, okay, in Lth phase, and after that it is the L plus 1th phase. So what is happening is that uh, so the Lth phase 1 is a little bit higher than this, okay, but if you are adding a small epsilon, okay, so then it becomes higher, okay. So and so that is why we are updating to this value, okay, little high, little bit, the combined value is little higher than the previous one.
Can you please confirm which assignment you were solving?
It is the week 2 actually, the PAC bounds one.
Okay.
Mm. So the probability that we get is quite high, 1 minus delta L, okay. So this is the scenario we have, okay. So I know we are moving a little slower, okay, but I will cover up, okay, the week 3 and week 4 part as well in a few next few sessions. Okay, these are later parts of the week 2. Uh, so this here we have the algorithms for the bandit problem. Okay, so for solving the bandit problem. Okay, well, I hope you got this one. Okay. Uh, so next we come to Thomson sampling.
Sir, can you explain that second sentence, sir?
Which
That
one?
previous one?
Yeah,
Previous one.
yeah. The second sentence. So second sentence, you can see the maximum of the rewards of the true breast arm in SL plus 1, that is in L plus 1th phase. Okay. So what does it mean? Maximum of the those Q functions are the reward function. Okay, and J is the is I is the arm actually. Okay. Okay. So if you move again, maximum of the reward of the true best arm. Okay, and in the L plus 1th phase. So this is the expression that we are talking about. Okay, okay, and other than that, you can see that this other options don't make much sense actually. Minimum. Okay, so maximum of the true rewards of the true. So A is the L plus 1 as they have told, so that's not correct. A is the Lth one. Okay, and B is the L plus 1. Okay, so that is why 1 and 2. Okay.
Okay, sir.
Hmm. Okay. So let's cover which of the following statement is not true about Thomson sampling or posterior sampling. Uh, Thomson sampling, as you know, so this is the occurrence that you have a reward, okay, and this is the probability
Uh,
density.
Hello, Anirvan.
Hello, yes.
Can you please write quite properly because so many words are not properly. I mean, it is visible but not clearly understandable.
Okay,
That's
okay,
why.
I will do that. Thank you. Uh, so this is the reward versus probability density graph, and so this is the illustration in the class as well. So so these are the probability distributions of the uh, distribution of the arms actually. So what I mean is, so the arms that you have here, okay, so the reward that you get from here, okay, can vary, okay, and I mean the, as you remember in the UCP that so there is a channel of which area does it lie, then after a sample this become closer, okay. So this uncertainty has been represented by the distribution here, okay, and so the point is that in Thomson sampling what we do, after we sample from this, okay, uh, the one we get as the best samples, we narrow it down and make a better estimation from that, okay. So if you narrow it down, the what happens, the variance is reduced, okay. If the variance is reduced of this, then it is easier to estimate the value, okay. So what happened that then the next sample we are going to get from here, it's like these are not overlapping, okay. So let me make it a better illustration, okay. So what can happen is that so something close, okay. So okay, something like that. So previously we are sampling from here, okay, and this one is from here, say, and next what we get after we have made it a steeper one, okay, so variance we have reduced, and mean has got increased. Something like this has happened. Okay, so now suppose in this situation I'm sampling or to make my point clear. So what I'm doing, suppose this has got steeper but like somewhat like this. Okay, now when I sample, so it is getting somewhere there. Okay, so now this is the best one. Okay, so narrow this one down. Okay, so and you keep doing it like that until this becomes very narrow with no variance and almost straight lines. Okay, like this. And so this is a clear answer, right? So this is the idea about Thomson sampling actually. uh, and so after each sample is drawn, the Q distribution Q star Q star distribution for sampled arm is updated to the closer to the true distribution. That is correct, right? We are moving closer towards a more definite distribution. Okay, and true value of the that has to be estimated. That is true. Okay, so I'm taking this one, but we need to find the not true ones. Okay, Thomson sampling has been shown to generally give better regret bounds than UCB. So it is actually correct. Means like in Thomson sampling uses a probabilistic method, which is computationally more expensive, but it gives better result. Okay, so this is one thing. In Thomson sampling, we don't need to eliminate arms each round to get good sample complexity. Yes, so in Thomson sampling, we are not eliminating any arm. In the next round also, we are going to have all 4 arms in this case, as you can see. Uh, so we don't need to eliminate. Okay, so you can see after odd one out, this is the answer. But let's explore this one as well. The algorithm requires that we use Gaussian priors to represent distribution over Q star. The thing is that we can use any prior actually, and most commonly beta distributions are used as prior. Okay, prior distributions, and but given the situation, you can take any prior. Okay, and the type of knowledge you have of the problem, according to that you can choose any prior. Okay, so Gaussian is not required. Okay, so this is the answer. So this makes this one the answer. Okay. Any doubt? No doubts. Okay, so let's proceed further. The confidence bound of each arm UCP algorithm cannot increase with iteration. So this question we actually have covered. Means similar to this one. Okay, uh, so UCP algorithm is this one. Okay, so in a UCP algorithm, what we have is that QJ. So J is that arm. Okay, here, and J can be any arm, not optimal or anything. Okay, Q is the reward function, and so we are adding this. We are adding this expression. Okay, which denotes that this is the uncertainty or uncertainty we have in estimating the true reward. Okay, of that arm. So n is the number of number of times that we have run the algorithm. Okay, so this is discrete on. Okay, so 1 2 3 4 like that. Okay, nj is the number of times the jth arm has come as the preferred one or the best arm. Okay, with the highest reward. Okay, so that is the nj number of times that has happened. So this is the expression we have for upper confidence bound, and so the confidence bound of each arm cannot increase with iteration. uh, so the point is that it can actually increase. Okay, so the arms which are not selected. Okay, so that for them this one will not increase, right? because uh, at step L, nj, okay, and at step L plus 1, because they are not selected, so this is still nj, okay. So this is not increasing, but this has increased from L to L plus 1, okay. So what happens is that for that this value has increased, okay, leading to an increase in the confidence bound, okay. Now we do not want to increase the confidence bound, the point is to reduce it, but it can increase at steps, okay. And the preferred arm confidence will keep reducing, but the other arms will keep increasing, okay. So that is why this is not correct, okay. And so nj terms in denominator ensure the confidence bound remains the same for unselected arms. It does not remain the same and decreases from the selected arms. It does make it decrease, but does not remain same for unselected arms, okay. So this is also wrong, so both assertion and reason are false, okay. Any doubt here? Any doubt?
Hello.
Yes.
Can you please share the screen?
Okay. Okay.
Please explain the second term, that uncertainty one term. Please.
The reason one, right?
The second one. No. The what you have written, no?
Hmm.
The expression. The
Hmm.
second term. That
Okay,
uncertainty
this
term.
one. Yeah.
This one.
So this is the confidence bound. Okay, or uncertainty you can say.
Yes.
So it is the square root of 2 times log of this n represents the number of steps we had taken. Means like what steps do I mean? So what we have is that we have this arms. Okay. Suppose three at this. Suppose three are there total. Okay. And so what we have here is that so some value of q for each of the arm, say here, okay, but it can go up to this or like that, can be below as well, okay. But the you can say estimated value at the previous iteration is this, okay. And and uh, the thing is that so I'm adding this value, okay. So under root value that you get, okay, so this is let's see it, let's say it is c, okay, cj. So this is cj, okay. And so when we compare, what we do is that, let's not say so after some iterations what happens that someone will increase, suppose here, and and uh, and something, some other may decrease as well, okay, something like that, okay. And the values can also go up and down. Suppose this value comes here, okay, and this value comes somewhat above, okay, something like that, okay. And so it can happen, okay. And then we are going to compare the maximum here, okay. Okay, the maximum peak we are going to compare, okay. Whichever is higher will be selected, okay, and this algorithm will be applied, this step will be applied, in which we are taking this one q, okay, and adding this, okay. So this is the updated q next, okay, and accordingly this is also added to it, okay. So this q will increase, okay, q will decrease, and the bound is also decreasing, okay. If we keep selecting the arm, then the bound will keep reducing and we'll get to a true estimation, okay. So something like this happens, okay, in UGB. And so in the case of this expression you understood. So nj represents the number of times that arm has been selected. We're dividing with that, okay. So because if you're selecting the arm, you get more information about the arm and the uncertainty will reduce, right. So the bound will reduce, and n is the number of times the total number of steps has been taken. This is that. Okay, clear?
Yes, clear. So the thing is, it is clear from the expression, but I'm not getting how that because logarithmic term. Ln whose argument is n. So number of times the experiment will be conducted, right?
Hmm.
So, uh, so if I take n is too large, then definite ln logarithmic value of n will be too large, right?
Hmm.
So, in this way, how this square root term will get decreased at every step, so that um, that average value, that q will we get that uncertainty will be reduced, and it will like just only qj term will exist. And
Okay, so the thing is that if the n is too large, okay, so
hmm,
given that situation, and suppose the nj has been sampled, means nj means j term has been taken very few times. Suppose n is like 10,000 and j has been taken like 10 times. Okay, so this is a situation that you want to say, right? Or what? And
yes, yes,
another situation can be that nj has been taken quite a few times, so maybe like say 5,000. Okay, in the case of 3,000, this is 10,000. Okay, so 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 if this is the situation, you cannot say like it is a very large number because those are
yes,
comparable. But in this
yes.
situation, so
Hmm.
this is a large number. Okay,
Hmm.
so so what you mean to say is that so what is the point after this?
So my point is, if you consider the first situation, then the logarithmic value of n will be large, right?
Hmm.
So then obviously square root will be lesser than the original value of the logarithmic term, but it is actually large after taking the square root
Hmm.
term
Yes.
also. Then how do we say that the uncertainty gets reduced, and that is only
So
qj term will exist?
after every step you take, so if
Mhm.
yeah, this is 10,000. Okay, so it one step I take, it becomes 10,001. So this becomes
Mhm.
11. Okay, so
Mhm.
still after if you take it, keep taking this one, so
Mhm.
this will keep increasing. Okay, and so resultantly, Acha, you're saying that ratio may not decrease, huh?
Yes, yes.
Sure. Mm.
Because it is always larger. As time goes increasing, it will always large value.
Hmm.
So how can we say that the uncertainty um, that bound is getting reduced, uh, and only qj term will exist? That I am not getting. Yeah.
Okay. So if n is large but nj is small,
Hmm. And comparatively, it is small, quite
comparatively
negligible.
small.
Yeah.
Okay.
Hmm.
So increasing this one, this is also getting increased. How is
Hmm.
the bound decreasing?
Hmm.
This is the point, right? So okay. So let's see. So the point to be noted is that n is equals to nj plus some, not including j. Okay, so you can write it like that. Okay, and okay, so this is the situation we have, and so next what we do is that, mm, right, now logarithm of nj plus n minus j, and 2 times is also there, divided by n square root of that. Okay, so nj. Okay. uh, so if it is like too large, n minus j is very large compared to nj. So let's check about. So this is the expression, okay, for the expansion. uh, so if we take common 2 log n minus j, and by some rule this will come log of nj 1 plus n minus j nj by n minus j. Okay, so I take this one common, and 2 times here as well. Yeah, 2 times here and here.
You are using the formula log of a plus b, right? So log
Yes,
of a
yes.
plus log of b. So
Yes.
log of b means log of n subscript minus j.
So I'm trying to actually, what I'm trying to do is, like, I'm trying to expand this one actually.
Okay.
Okay. Okay. So you can use the expansion rule here, Maclaurin expansion here, and this becomes, expression is nj n minus j minus square of that dot. Okay.
Yes, logarithmic.
So
Logarithmic.
this becomes this. Okay. So this remains.
Mhm.
Okay. And now the point is that I try to divide by nj. Okay. So
Mhm.
this will be divided by nj, and this will be divided by nj. This
Mhm.
will be also divided by nj. Dot. Okay. So this becomes
Only n minus j. Yeah.
hmm, okay.
Yeah.
And now
Mhm.
what I'm trying to do is, I'm trying to increase nj. Okay. N minus j will remain fixed, right? Okay.
Mhm.
This will
Mhm.
reduce for sure.
Right.
Okay. And now you must understand that n minus j here remains fixed. Okay. And if
Mhm.
you see the square of this, okay, you can say this is like goes to 0, becomes very
Yes, yes. Got
unimportant.
it.
Okay.
Yes, yes, got
So
it.
this
Yeah.
is fixed. Okay. And this one
Mhm.
reduces, so overall reduces,
Mhm.
right?
Yes, yes.
Okay.
So the main crux is that n is represented in terms of nj plus n of n minus j, right?
Hmm. So then you can explain it better than if you take the n part. Okay.
Mhm. Yes, yes. So the n minus j represents that uh, the
No,
arms which are not selected.
Anna, n minus j represents that these are the number of times that the jth arm was not selected.
Uh-huh.
Okay.
Number of times. Yes.
Correct. Everyone understood?
Yes.
Okay. Uh, any doubt here?
No, it is clear.
Okay. Okay. Let's move on. Um, so the point is that we're using the naive PAC approach. Okay. In a 10 arm bandit problem, so there are 10 arms, 100 sample. We need 100 samples for getting this. Okay. how many samples would be needed if we rerun the knife. Acha, the epsilon is halved, giving the delta unchanged. So epsilon was first epsilon, next it becomes epsilon by 2. Okay, now the point is that how many samples would be now required. Okay, so in the naive PAC approach, the number of samples that have to be taken are given by 2k by epsilon square ln 2k by delta. Okay, so you must understand that number of k is the number of arms, so these are fixed for the two scenarios. Delta is also fixed, ln, so this quantity is fixed. Okay, and this is also fixed, so only the quantity that is varying is epsilon. Okay, so this quantity was previously 100. Okay, right, and so this total quantity I meant to say. Okay, now what has epsilon has become half. Okay, so epsilon by 2. Okay, the square of that is epsilon square by 4, so 4 comes up. Okay, this is 4 times of the previous value, so 400 is the answer. Okay, so 400 is the new value. Any doubt?
Sample, just a minute. Probably I skip the term. That is epsilon. Sorry, what is K is 10, right?
K is the number of arms in the bandit
Yeah,
program.
10, 10,
Yes,
10 arm band, 10. Yeah. And delta is the samples, right? We need 100 samples. No, no, no. Epsilon, delta, uh,
epsilon delta
just
are the parameter. Means like delta means that the in the pack situation, what so let me go to my previously done. So what we have here, okay, so here in session 2, what I explained, I did explain the pack pack optimality somewhere. I might not have uploaded the uh, acha. So this is the pack optimality. So in pack optimality, what happens is that the optimal arm is A star. Okay, and Q star A is the optimal estimation of the reward function. Okay, so what we mean to say is that this if for any arm for the reward function will be greater than the what do you mean, like reward, perfect reward, that is correctly estimated reward for the best arm. Okay, so it can become greater than this one. Okay, only if we subtract a small epsilon value, and this leads to a high probability 1 minus delta. Okay, so in this situation, what does it mean actually? Means that so this is maximum, right? This has to be maximum. Okay, so what we are saying is that we subtract a small value epsilon here, so then we will be getting an arm greater to this, let's say A, and the probability of that happening is 1 minus delta. Okay, which is a high probability. So the pack optimality, what was that for? That A star, you need to estimate a star value. Okay, but you don't know what is A star. Okay, so this A is an approximation of A star. Okay, and the probability of success rate of the approximation of max is 1 minus delta. Okay, high
With chosen epsilon. With chosen epsilon.
Yeah.
So given epsilon. So epsilon value should be larger.
No, epsilon value should be small. Epsilon delta, both should be
Ah,
small.
yes, yes, sorry, sorry. Yeah, it should be small. Right, right. Yes.
So that is the situation of PAC optimality.
Hmm.
From that we have got to a PAC algorithm for solving the bandit problem. Okay. So that is how it progresses here. Uh, so from that we have got epsilon integral. Any doubt?
No, it is clear. Someone is mic is on. I think the noise is good. Yes, back
Any doubt?
optim. Hmm. Now it is cleared. Yeah.
Okay. So these are the parameter epsilon delta. Okay. From the PAC optimality condition we are getting that. So what is true about the median elimination algorithm? So median elimination algorithm I have explained before. Okay. I think handwriting wasn't too great here. So so let me go through that again. Okay. So what is true about the median elimination algorithm? Mm, so it is a regret minimization algorithm. So that is not true. Okay. So regret minimization was for selecting which arm to okay, so regret minimization, okay, we can get to that. I think I've explained this one as well somewhere. Okay. So it is not a regret optimization regret minimization algorithm. So with regret minimization you can get to optimal arm. Okay, but regret optimize, was any of the algorithm regret minimizing one? Nah, none of the algorithm was a regret minimization one. So it is not a regret minimization one because we are not calculating the regret term, right? Uh, how much is the, so regret was this, okay, that, so you have the payoff or reward that you get. So how long does it take to get to the perfect reward? Okay, so this is the regret. Okay, so if you want to minimize and get to the right term quickly, okay, so the regret will be less. Okay, so that is not the point here. We we get to the right term is the important one. Quickly is not the point here. Okay, the probability of EL optimal arms of round being eliminated is less than del L for the round. Okay, uh, so it is something like this. Okay, that, so So the point is, you can understand this, what is EL and del L for the round, what does it represent? So L here, so L here represents the level, okay. So what does level mean here? So level is the how many steps you are taking until you get to that one arm, okay. So LF level means L steps are taken, okay. So at that round, okay, epsilon and del are epsilon L and del L, okay. So in the algorithm, the thing is that so so the del and epsilon does not remain fixed in the median elimination algorithm. So what is happening is that so what you're first trying to do is that we have a, like you can say, repository of arms, okay, after L steps, that is called SL. So they're like, suppose that we started with 100, okay, after L step only 50 are left, so 50 arms are there, that is represented by SL, okay. And so that is that, okay. So we start with so first S1 is A represents all the arm, okay. So this is the initial condition. Next epsilon 1, this is the initial condition, is epsilon by 4, okay. That is how they started. Del 1, initial condition for del is del by 2, and L is equals to 1. So L equals to 1 is like obvious, the first step, okay. And and how do we estimate the reward after that step? After one step is represented by 1 by del by 2 square log, this is QLA. So reward for arm A after L step, okay. So 3 by del L, okay. This is the reward for that, okay. This is the estimation of the reward, okay. And so next what we say is that so next we find the median value of the QLA, okay, and represented by ML, okay. And now next what we say, that when we are updating the SL to get to SL plus 1, which is the repository of all the arms that we need for the next step, so what we are doing is that for any arm, if this value, okay, uh, and and of course, like ML that we get is for the optimal one, and for the uh, for any arm, this Q value should be uh, if it is less than ML, okay, so then we take it to SL plus 1. So those arms are taken, and after that the update step is SL. So for the next step, the new parameters are epsilon L plus 1 is equals to 3 by 4 epsilon L, okay, S L plus 1, no, not S, del L plus 1 is equals to del L by 2, and L is equals to L plus 1. This is the algorithm. So we repeat until S L is cardinality of L, okay. This you can say mod type brackets is called cardinality, becomes equals to 1, okay. So S, you can say, as I said, it is the repository of all the arms, okay. So cardinality, what does mean? The number of arms there are is represented by this, that is equals to 1. So this is the median elimination algorithm, okay. And so this is the situation we have, okay. And the probability of epsilon L optimal arm being of round being eliminated is less than del L for the round, okay. So the point is that the optimal arm after that many steps, L steps, should not be eliminated, right? So the probability should be less, okay, and the probability is less than del. That is what they uh, have in this statement, okay. Optimal arm should not be rejected, of course, uh, so the median elimination algorithm also, like in the proof of the algorithm, the important part is that we prove that this the situation of rejecting the optimal arm after L steps is very less, okay, and so that is why this algorithm is supposed to work well for every situation, okay. So the point is that now what we get is that uh, so so the point is that means the derivation is not easy, means it's not too hard as well, okay. So the point is that means like so this so the optimal arm is being eliminated, okay. So eliminated means that we're taking some non-optimal arm, okay. So I represent the non-optimal arm by J here, okay. And the optimal is as always represented by A star. So L is the lth phase, okay. So what I'm going to write is Q, this reward function, QLJ greater than equals to Q L A J A L, or maybe just you can write so you can understand it. So this is the one. So if it is greater, okay, so this is the bad situation, okay. So which means that our good arm will be rejected, right? So that's the important thing, okay. And another bad situation that we have to inculcate here is that uh, so we get to this situation like this. They had to be explained earlier, but okay. So another situation is this one. So event 1 E1, okay. So this represents that so Q is the reward function, okay. And epsilon 1 by 2, epsilon L you can write, okay. L you can write, okay. And this becomes, okay. So this is one event, okay. And okay, and so what we're seeing in this event, you can understand, is that so it is our like estimation of Q, okay, for A star, okay. And this Q is the true reward, okay. And so what we are doing is what we are seeing here is that this so this Q star grossly underestimates the true value, okay. Even after subtracting some, okay, it is still greater than the estimated ones. The true ones is still greater than the estimated ones, so they are nowhere close. The true one is much greater, okay. So this is the situation we have here, okay. And next so the point is that So now the point is this probability of epsilon 1 of this event E1 is less than equals to del 1 by 3. Okay, so this is one result. Okay, and we get this from Markov inequality, I think. To prove it, acha, so proof I don't know now. I think from Markov inequalities. So next what we do is that, so this is one bad situation, okay, and we write the so this is actually a good situation, okay, or am I correct? And so we write the opposite of that, so that becomes a bad situation. QL AL star greater than equals to Q star AL star minus epsilon L by 2. Okay, so these are the two situation or situation, as you can see both are bad situation. Okay, and this is the bad situation we're interested in because we're eliminating the true arm, okay, in this situation. Okay, so what I do is that, so next they see this for the first iteration only. Okay, so this is del 1 by 3, and this is also not for the LH situation. First situation only. Okay, and so this is how we get there. And next what happens is that that so next in the proof, the thing is that expectation of this our desired bad situation, which we want to calculate. Okay, and our rest of the expression, okay, this is less than del L mod into del 1 by 3. How I've got this one, I don't know. Del L by, acha, we have got this one from this actually. So the point is like how am I getting this expression and this one? So actually this is from the this is from this equation, the what do you call this, Chernoff-Hofting bound, okay, and which from which you can get this, that probability of Sn, which is this one, okay, Sn, and this is mu, which you're trying to estimate, okay, and this is some epsilon, okay. So that probability is equals to e to the power minus 2 epsilon square pi multiplied n is the number of steps, okay. So here it is L, so L is epsilon square, okay, and so what is this, is this so this is the L part, okay, which comes out to be epsilon square, okay, and into log of 3 by it went. So this is epsilon square into log of so right here it is log of okay, I'll write the full expression again. So e to the power minus 2 epsilon square, and the L value is epsilon square into log of 3 by del L, okay. So what happens, this is gone, this is gone, so you take the, and the 2 is also there, okay, you remember the expression. So 2 or 1 by 2, I think 1 by 2 will be 1, okay, and so this 2 is cancelled, okay, this epsilon square is cancelled, minus is there, okay, so minus so due to minus is because del L by 3, okay, log, so exponential of log, okay, so what happens, this will be del L by del 1 by 3, okay, and you again use this one here, okay, to get the bound for this expression, which comes out to be del L by del 1 by 3, okay, like that, from the Chernoff-Hofding bound, okay. And next what you do is that next what you do is for the probability calculation, you calculate this is greater than equal to del L by 2, okay. Means like it is we are taking also a precaution that this bad situation occurrence is very small, okay, and okay, so the net using Markov inequality, what we do is that from the Markov inequality you can see that Markov inequality explains that Markov inequality here explains that P of x greater than equals to A is less than equals to expectation of x by A, okay. So expectation was this, okay. So for the probability, this has to be divided by del L by 2, okay. Del L cancelled, this becomes 2 del 1 by 3, okay. So like that. I know it was too complicated, but okay, so getting to the problem. Hard to find the problem now. Okay. Acha, in this problem actually they are asking for this. Okay, so this is so it is less than del L. Okay, and the expression is accurate expression is 2 del 1 by 3. Okay, uh, so so that is why it is correct. Okay, so this is wrong one. Okay, this is the correct one. So it is not guaranteed, but the chance of going wrong is very low. Okay, that is why it is wrong. And if you replace by epsilon by 2, it doubles the complexity. It does not double, it becomes 4 times. Okay, because it is by epsilon square is there. Okay, so if it doubles, if it becomes halves, then the total becomes 4 times. Okay, so this is also wrong. Only this option is correct. Okay, any doubt?
No. Anirban, can you please explain the question number 5 because I missed because of late joining. My actually what answer I chose that was wrong. That's why I'm
Here,
asking.
huh?
Then this assignment only.
This is the one, this question.
The equality inequalities for the UCB algorithm. TI and that one. Just let me check.
Acha, that
You.
question from the. Acha. So let's check that one. Okay. Uh, this one, huh?
The five. Yes, yes.
So some inequalities, equalities for UCB algorithms are there. So let's check this one. Okay. So this is the question we have.
Mm-hmm.
Uh, so so how many of these inequalities are correct? Actually, the point is that. Okay. So the thing is that I think two should be incorrect, right?
One,
Let
two,
me check this one.
one and two are incorrect.
No, first one is correct. You see, the first one is
Oh, no, no, no. Sorry. Yeah, yeah. First one is correct. Right,
first
right.
one is correct.
Yes.
Why? Because for ayat, uh, uh, so action I am talking about. So what happens is that suppose there are k arms. Okay. So first for every arm one times we have taken that arm. So for ith arm, okay, so we take one first. Okay.
Hmm.
Next
Hmm.
for after that k plus 1 to n sample means steps that we are taking, how many times I will be taken, is that how many times I is taken. Okay, so means like this is a trivial one. Okay, actually that eh, that many times it is equals to I, means the arm is I, that number has to be added to ti. Okay, so this one is correct. Okay, that's for sure. Okay, next next tin is equals to m plus m equals to 1. From 1 we are checking. Okay, so this one is also correct. Okay, why? Because we are checking every time it is equals to I. Okay, so this one is also included here. Okay, the case steps in the first k steps only one time will happen, so that is the one, that is why the one is there, but it is more you can say hidden form. But this is also correct. Why? Because 1 to k steps, okay, only one time it will taken. So this both statements actually same. Summation starts from m equals
Yes.
to 1 here,
Hmm.
and it
Hmm.
start from k plus 1. Okay,
Mm-hmm.
so this is also correct. Okay, so wait a minute, someone is trying to join. So the point is that next what we have is, so next what we did here is that, uh, so in the UCB algorithm, what we do that this is our estimation, this is our the confidence interval. We have added this one. Okay, so in the both, so what you're taking for I arm, which is not optimal, and this is A star for optimal one. Okay, so what you're trying to do is that for so so we'll take the ith arm when, because we'll take the ith arm when this confidence interval and plus the q of the ith arm is more than the a star one, right? So that is when we are going to take the ith arm. Okay, so that many times from k plus 1 to n plus 1. Okay, so this is also answer, right? Correct? Any doubt?
No, no, it is right. Yeah.
Okay, so next what you're going to do is that, uh, so we're comparing this one. Okay, that, so here the fact is, okay, so we're taking top of this for the ith one. Okay, but only taking the middle value, estimated value for the a star one. So is this the correct one? UCB, what happens? So it hello. Uh, so it is the correct expression, because like, let me explain. Is it wait a minute.
I got it. Actually, all the answers are correct. I was confused in one part.
So
That is
last one,
clear.
what is the explanation then?
The last one, I think, last one is the similar to the third one, just only intermediate. That additional part is
Sure. Uh,
that C m minus suffix m minus one. T a star m minus one is not in the fourth option. So, because if we go to the third option and that the term c m minus 1 t star m minus 1 gives some additional value, right?
hmm.
And in the fourth case, if we omit that part, it is always be I mean, the condition will always be true if we just omit the additional value.
Acha, acha. Hmm. So what you're saying again? Repeat.
So I'm saying in the third option, the uh, the the third and fourth options are almost equal. Only the additional part is the c m minus 1 t a star m minus 1
Hmm.
is in the third option, right?
Hmm.
So that term gives some additional value, right?
Hmm.
and in that case the condition is true. If we just omit that additional value, in that case also the condition will be true.
Correct. That is the explanation. Yes.
So I have just one, and it is not related the assignments. Just only for clarification, I am I have one doubt. So just I am asking one L keyword problem that is related to reinforcement learning, but not from the assignment. So in LQR problem, we just define cost function, right? And if we try to define the reward function in terms of cost function, suppose our cost function is J is something, the state and that control functions, that X Q X
So,
transpose.
how about we solve this problem? Just one is left.
Yeah, sorry,
How about you solve this problem? Then you go to your problem.
I didn't get your question.
I
Which
mean, like,
problem?
just from my list, only one problem is left here. How about you solve? We solve this problem first, okay? Then we go to
Which
your
one?
problem.
Which one?
So this is the question actually. Posterior sampling, Thomson sampling.
Which question?
So you can see in the screen, right?
Just a minute.
Open your screen, you can find one problem.
This problem is from assignment.
Yes. So
Just let me check.
uh,
Just give me some time.
so just you don't need to find the problem. Just the thing is that it's a good problem. So see how it is done. Okay. Uh, okay. So what we have is a non-stationary bandit problem. So the reward function of each arm changes with time. Okay. So we are using posterior sampling. Okay, to pick the correct arm, which reduces which variance of each distribution of each arm and get to a estimation. So what are the likely changes that need to be algorithm so it adapt to non-stationarity? Okay.
So in yeah. So the non-stationary problem means like our
The reward
the
functions of the distribution.
samples are not equal from the same distribution, right? This is non-stationary problem, right? Huh?
Non-stationary problem is not that. So the reward that for each arm that we get has
Huh?
the distribution of that changes with time. The distribution keeps changing with time. Okay.
So distribution is not same.
Hmm.
Yeah, yes. For the reward, right? Yeah, yes.
So our problem is that
Hmm.
what can be done to the algorithm of the Thomson sampling so that it can adapt to non-stationarity, because in the case of Thomson sampling it is for deterministic case, not for uh, non-stationary problem. Okay. So they have told that update the posterior rarely, so that is not going to work. Okay, because we need to update it uh, regularly to take care of the
Yes. Hmm.
stochasticity.
Hmm, hmm, hmm.
Okay, and randomly shift the posterior drastically from time to time. That's not going to work because like drastically it can change the problem itself a lot, and randomly you don't know how much randomness is required, so that is very vague. Okay, so we are adding slight noise. So the answer to this is very popular. We add slight noise to the distribution, reward distribution, so that it cannot easily like narrow down the distribution, like it narrows down. So it cannot do that easily, because with the small noise, small noise is not going to change the problem like the second option, but it is not going to make it different from time to time, so leading to not such a easy estimation of the reward. uh, so so it takes more steps to converge, okay, but that is important as well because non-stationarity, the distribution also keeps changing, okay. It has to adapt with time, uh, how the distribution is changing.
So
For that,
this when this
hmm,
yes,
okay,
yes, you complete, you
so
finish
for
first.
that we need to add a little bit of noise, so it continues and it converges slower, for slower convergence, that is required, okay.
Uh, so when distribution, we say that distribution is changing with time.
Hmm.
So does it mean that it is known unknown distribution or known? I mean, we always consider that. I mean, usually known distribution like Gaussian distribution. So here, what does it mean actually?
I mean the distribution of reward for each arm is actually changing with time, and we actually don't know anything how it is changing. You know, if we had known how it is changing, we can just model that one. We have no idea how it is changing. Okay, but still in this
So
situation,
distribution is unknown. Distribution is unknown, right?
distribution may be known. What we say Gaussian, then its
Okay.
parameters mu and variance is how is it changing? I don't know.
Okay. Okay. Achha, achha, okay.
Maybe
Okay.
known as well. You know,
Okay.
maybe
Got it.
unknown.
Okay. Okay. One trace posterior sampling. Mm. Keep adding a slight noise to this variance. Mm.
Okay, done. Done.
Yes. Just one. I mean, just not from directly assignment. Just random. I mean, I have one doubt. Like, if we choose a reward function, it is not a value. Just not a uh, any numerical value, just function. Then is it necessary that it is the reward function will always be like twice continuously differentiable or once continuously differentiable? Is it I mean the is it the necessary criteria to choose any reward function? I mean, is there any
So
necessary?
the thing is that we are not actually choosing the reward function. Reward function for the problem is already inherent with the problem actually.
Yeah, so in that sense, uh, I mean, choosing means we are defining, like, suppose we are defining cost function, so and we define our reward function as the cost function. In that sense, I am asking, okay, is it
So reward
necessary?
is a distribution actually. So not always can you write is that as a expression, okay, as a function. Okay, and now and cost function is not at all possible because you see we are not trying to reduce it. You know, cost function, okay, we try to reduce the cost, okay, but the
Yes, yes.
reward is a distribution from which we are sampling the rewards after for many steps to
Mm-hmm.
have an estimate about which arm is the best to choose, okay.
Mm-hmm.
Okay, so we were actually not trying to minimize the cost anyway. You know, the distribution is inherent, you know, we are not even trying to predict the distribution, we just trying to get to an estimate for the best arm, okay.
Mm-hmm.
So what happens is that after for a, once like in previous lectures we have explained, like at every step of sampling from of the reward changes. You know, reward will not be same after every step, even in a stationary distribution. So the reward means like, so this is the distribution. So for one arm, okay, Gaussian distribution say. So first I sample, I got sample from here, okay. So this is the reward I got. Next I got a reward here. Next I got a reward here. So the probability is higher here. So means if I sample suppose 10,000, most of the samples will be here. Some some sample will be here. So the sample what this value represent the reward. Okay, how much reward to give. Okay, so that is the point. Okay, but the reward is changing. Okay, as we sample, and in this case of non-stationary distributions, the reward changes, that's for sure. Even the distribution keeps changing like that. If it remains Gaussian with time, but the mean and variance will keep changing like that. Okay, so this is the non-stationary distribution situation.
Hmm.
Okay, any doubt? Got it? Any doubt?
I have no doubt.
Okay,
Just so uh, I mean, can you please suggest any like reinforcement learning? I mean, coding platform using in Python. So just we asked you in the earlier
the
session.
point is that you can find the problems like coding assignments in Kaggle actually. Kaggle, the
Where?
problems will be there.
Sorry, where?
Kaggle is a website, in which there are machine
Kaggle.
learning problems. Okay, so you can find machine learning problems there. Okay.
Kaggle.
Hmm. Kaggle challenges are there. Okay, so there you can solve. Okay, so this concepts will be used. You have to code and solve the problem. The data set will be given like that.
It is Kaggle.
Yes.
Kaggle machine learning.
Just Kaggle is the website name. So done. Any problem? Okay, so we close the meeting for today.
Sir, previous, sir,
Huh.
fourth assignment, sorry, third assignment.
Third assignment we'll do it in next class. Okay.
Okay.
Okay. Thank you very much, everyone.